Okay, welcome. This is the fifth online event of our raw machine learning meetup. So we are a group of people who love machine learning and data science. I'm particularly happy about this event because we have two great international speakers. So we have Matthew Johnson, who will talk about Jax, and Michela Paganini, who will talk about her work in the lottery ticket hypothesis. Both talk will last around 30 minutes, and then we'll have approximately 10 minutes of question answers. If you have any question during the talk, you can write it in the chat so as not to interrupt the speakers, and I will try to read them during the talk or at the end, depending on the questions. The recording I'll upload it on YouTube on our channels in the next days. So again, welcome all of you, and I leave the word to Matthew for his presentation. So I'll stop the recording, sharing of my screen. I'm very happy about this talk because it's quite a while that we talk about Jax in our channels. So having an official talk is quite a...
Yeah, and thanks for the invite. In fact, I think some of you may have written like one of the first like blog posts about Jax.
It was me, actually.
Yeah, it was really exciting to see. I think was it like January in 2019 or something?
Yes, actually, it was me in Italian, and then a friend that helped me translate it in English.
Yeah, we had a Italian-speaking friend translate it for us, actually, and it was really exciting because like we were really impressed at how much it was extremely early on. Like we had just put out Jax, we were like, is anyone going to understand what this thing is? And it was like amazing at how, I don't know, it's just a beautifully put together post, and it was like, man, they're really, at least someone is getting it, this thing. Yeah, great. So thanks so much for the invite and for that, and for the opportunity to speak here. So I'll present my screen, and please interrupt and yell at me if if you can't see things, but otherwise I'll proceed as if you can see. So I have a few slides and a bit of a demo, and I'll start a timer so I can stick to the time. But I'm especially interested in any questions you all have, because that's always it's great to dig into whatever you're wondering about. Great, so I'll talk about Jax. This is of course not just work by me; it's work by the entire Jax team, which is ever growing. So to start to motivate Jax a bit, you might ask, how would you write a performant and even scalable deep neural network from scratch in Python? Like, what are the actual ingredients that we need to do it from scratch? So to start off with, we can start with NumPy. NumPy is the standard of doing array computations. That's certainly what I used in grad school, and it's really easy to express a simple neural network in NumPy. In fact, maybe you just have to write a function like this. This is implementing a fully connected MLP. We're just have to call NumPy dot, vector addition, and do some element-wise nonlinearities. And this is really all a basic neural network is. And then to train the parameters, here a list of weight matrix and bias vector pairs. We need to have a loss function. And so here, just a trivial sort of squared error loss function, also very easy to write in NumPy. And so you might wonder what is missing. Why is there all this hubbub about TensorFlow and PyTorch and Theano and all this? Why weren't we just happy with NumPy? And there are a few missing ingredients, even though it's so simple to express the basic computations in NumPy. One of the missing ingredients is accelerator hardware. So as you all know, GPUs and TPUs, basically like specialized hardware, makes neural nets much faster to evaluate and indeed to train. And this has been, being able to scale up neural network size has been, key to the revolution of deep learning. Was there a question or anything? Sorry, I thought I heard something. Great. So another missing component is we want to be able to do gradient-based optimization, meaning we want to be able to compute gradients of this loss function with respect to the parameters. And automatic differentiation has also been powering the sort of revolution that we're in. So we need some kind of an auto diff that NumPy doesn't provide. Other things we might want to ask for are things like optimized compilation, doing optimizations like fusion of operations. If you look at this loss function, we're doing a lot of element-wise operations, and if we sort of just evaluate this sort of in the NumPy mode of just applying one operation at a time, we'll end up sort of loading these big arrays from memory, doing a single operation, and writing the big arrays out again. And then maybe to do the subtraction, and then we need to do this element-wise squaring. We need to like load everything in from memory again, do the squaring, and save it back out. And these accelerators are often memory limited, especially when we're really trying to push the frontiers of research. So doing things like operator fusion, or even starting to optimize the memory layouts, like how you lay out all the tensors and arrays in your program, or being able to say, hey, my accelerator has limited memory. Maybe I need to be able to fit this computation. I need to decide, well, here's an array that's easy to recompute, so I can rematerialize it instead of having to store it. Doing these kinds of optimizations are another missing piece from just being able to write this execute this kind of code in a performant and scalable way. And then finally, I think some of the most exciting deep learning results have been really constantly pushing the scale of computation. I think the work on GPT-3 and this G-Shard paper that came out of Google recently, those are, I think, really exciting about pushing the scale, and how do we be able to write code like this and scale it. So Jax is really about providing those missing pieces. And just to jump through sort of one by one, starting from this NumPy program as I would have recognized it in grad school, the way Jax gives us these pieces is, first of all, when using Jax, we have a sort of NumPy API. So if you import jax.numpy as JNP, you can see I've replaced all the NumPy calls with JNP. And this actually already gets us somewhere. This already means that these operations will be, when we apply these functions to inputs, they'll be executed on your accelerator, so on your GPU or your TPU, without changing anything else about the code. So that's pretty cool already. But there's a bit more than we need. There's autodiff that I mentioned, and Jax has autodiff. Here is our sort of basic gradient function, and here's how you'd apply it sort of at the bottom of the screen. There's more that Jax offers that is important for certain kinds of gradient-based optimization and machine learning. There's this VMAP function, which I'll talk more about later, but it can do things like give us very efficient per example gradients, which are important in some differential privacy applications. Then there's end-to-end compilation. So Jax has this JIT function that does sort of stages out computations from Python to this XLA optimizing compiler. And it'll do all those optimizations that I mentioned, like layout optimization and fusion. And then finally, if we want to parallelize the evaluation of this function, we have this PMAP operation, which again, I'll dive into more, but at the high level, this is a simple way to program multiple GPUs or multiple TPU cores. So this is sort of our Jax in one slide. I want to jump into a demo. But first, maybe just a brief comment on the sort of philosophical underpinnings of Jax. You can already see maybe in that Jax in a single slide example. The sort of thesis underlying Jax is that numerical computing is about expressing and transforming mathematical functions. Expressing is like what we had at the very beginning when we just wrote NumPy code, where we saw that NumPy programs are an effective way to express the computations that we mean for neural networks. It's actually quite easy to express things. And so the idea is that we think the problem of expressing programs is largely solved by models like NumPy. What NumPy doesn't offer us are ways to transform functions. And by transformations, more will become clear later, but one canonical example is autodiff that we're all familiar with. we sort of use autodiff as a user-wielded transformation where you write one Python function and then you are able to apply this transformation to get a new function out. The thesis behind Jax is that actually there are more transformations that are interesting and powerful to expose to researchers. And so that's why Jax, as you'll see, hopefully is a system. It's in fact an extensible system for being able to write and compose these function transformations on top of Python and NumPy code. So hopefully all that abstract stuff will become more clear. I want to show you guys a bit of a demo. Again, please jump in and yell if this text is too small or something like that.
There's a question in the chat. Do you want it now, or do we collect it all for the end?
Let's wait for the end just so I don't totally run out of time.
Okay.
That's okay. Great. So here's going to be a sort of lightning demo of Jax. This is on a cloud VM on the fine Google Cloud product, which you can start running your machine learning work on. Great. So let's just import jax.numpy at the top, and then we'll also import a library for generating random values. And let's start just by sampling a big 5,000 by 5,000 float 32 array. And we're just going to use this as sort of input. So what can we do with this array? We can do NumPy stuff to it, right? So we can call np.dot. I just ran these things. Let me do. Great. We can run np.dot to do matmols. We can do indexing, and we can print values and this sort of thing. Actually, it looks very much like we're using regular NumPy. One of the hints you might get that this isn't just regular NumPy is if you look carefully at the objects we're working with, at their repr method, you can see actually that this prints out not as an ND array, but as a device array. This is like a Jax value, and we call it a device array because it's backed by device memory. The sort of values in this array sit in device memory, and so when we apply operations like dot or indexing, all that can happen on the device. In this case, on a GPU, and values are sort of only pulled back to the CPU when we need them for something like printing, like we did here, or plotting, or Python control flow. Otherwise, they're left sort of lazily on the device for efficiency, so that when we apply NumPy operations, we don't have to do any sort of transfers. So as I mentioned, we can do NumPy stuff like plotting, and it sort of just all works behind the scenes. More NumPy stuff. I think I failed to clear these outputs again. All output clear. That's what we need to do. Great. We can do NumPy stuff. We can multiply arrays by their transposes. We can do all kinds of indexing. All of NumPy's fancy indexing modes are supported. So we had to learn a lot about those. So it really just looks like running NumPy code. In fact, again, you really might not believe that this is running on a GPU behind the scenes. Except one experiment you can always do is you can time things. This is quite a big array, and we can import the original NumPy as ONP and see how fast it can multiply to 5,000 by 5,000 arrays. This is a pretty beefy VM with like 64 virtual cores or something like this. So it can do this in like 261 milliseconds. This is using MKL. So that's fine. Of course, it can't keep up with a GPU. So if we run the Jax NumPy dot, which we've imported here as NP, we can see that it runs the same operation of multiplying two arrays in about 18.5 milliseconds, something like this. This is why we like GPUs, because they're quite fast at multiplying big matrices. Part of the key to deep learning. One thing I'll mention here is the little block until ready call on the end. You notice that we didn't need this before when we were multiplying arrays and printing out values. This is really only useful for sort of timing micro benchmarks. The idea is that Jax by default is asynchronous in its operation. So when we say, hey, multiply these two matrices, as soon as we sort of dispatch that operation to the GPU, Jax returns control to the Python thread, so it can proceed and sort of do more work. And by doing that, we're able to sort of let the Python thread run ahead, or overlap the Python interpretation with the execution of the work on the device. So that is good for efficiency. However, that means that if we want to do timing micro benchmarks and make sure that we're waiting for this operation to be done, we need to say actually block the main thread until this result is ready. Otherwise, we'll just be timing dispatch time, and this time will be actually a lot smaller because it's not timing the time that it takes to do the matrix multiplication. Great. So that's like, hey, a good way to run NumPy on GPUs or TPUs. My grad school self would have killed for this, but actually nowadays this isn't so surprising. We're used to a lot of libraries being able to do this. So you might be wondering, like, what else? What else can Jax do? I'm glad you asked. There is in fact more. I just want to go through a few of these function transformations just to give you an idea of how these work in Jax. So to start off with, let's look at automatic differentiation. So we like to say that our transformations have a one function API. We like to say that the Jax, using Jax basically looks like using NumPy, which presumably many of us are already familiar with. Plus for each transformation, there's just one function you have to learn. For reverse mode autodiff, maybe the only function you'll ever care about is grad. It's a higher order function. So it'll give us, if we give it a Python callable that evaluates a mathematical function, it will give us back a new Python callable that evaluates the gradient of that mathematical function. So here's one such, Python callable that evaluates a mathematical function. You can see it's got some Python control flow if x is greater than 0, and has two different expressions. So we can call this on random values, and we can exercise both sides of the conditional, and you can see Jax has no problem differentiating through Python control flow. And also, because this is a higher order function, makes it really easy to compose up higher order autodiff. So basically, grad can consume its own output. So you can keep calling grad, and you'll just be doing higher order autodiff of the function. Obviously, this is a very toy example, but it's really powerful just to be able to trust your autodiff system and be able to easily compose up higher order differentiation. So with that, with GPU-backed NumPy and grad, we can already do some deep learning. Here's that code from that first slide, where we have a simple, fully connected network and a simple squared error loss function. This is just code to run to sort of initialize some random parameters and random data, just synthetic stuff. We can, now that we have our parameters and our data, we can look at what the loss value is for our randomly initialized network on this random data. And we can run a little gradient descent loop to try to minimize it. So gradient descent is really simple, right? It's just grad of your loss function. Grad differentiates with respect to the first positional argument by default. So this is sort of taking the gradient with respect to the parameters. Here are all our parameter gradients. Then we can write a simple loop that'll just take a small step in the direction of the negative gradient to try to minimize our loss function. So I just ran that, and then we can see that the loss has gone down, right? And that's really all all there is to deep learning in a way. I'll run it again. The loss has maybe gone down a bit more. So that's really Jax basic autodiff. There's actually a lot more that I won't have time to go into, but that we've explained in this autodiff cookbook here. In particular, so we've been working on autodiff for a while. I mentioned that grad uses reverse mode. Actually, Jax has both forward mode and reverse mode. These are sort of efficient in different situations. And you can compose them up arbitrarily. This means that Jax is really good at computing things like full Jacobian matrices or Hessians or fast Hessian vector products, which are useful in sort of like advanced algorithms. Jax is also really good at autodiff in the context of complex numbers. So you can differentiate both holomorphic and non-holomorphic functions with it, and sort of everything just works. We're keen on things like supporting complex number differentiation because we want to be able to support as many research use cases as we can, and not just in deep learning, but also in general science, where maybe in other fields like of science and engineering, complex number and derivatives come up. In Jax, you can always sort of reach for our autodiff tools and be confident that they'll work for you. Great. So that was reverse mode autodiff, at least scratching the surface. Let's talk about another transformation. Let's talk about this end-to-end compilation that I mentioned. So we've talked about how Jax under the hood will be executing your operations on the GPU. One way to think about that is that we sort of JIT compile all the library calls. So like when you call into a NumPy function, maybe that'll be JIT compiled under the hood. But we surface the sort of JIT compilation transformation that we use internally so that you can also apply it to your own code and thereby sort of stage out bigger chunks of your program to XLA and get more optimization. If you like, XLA is this incredible piece of, XLA is the optimizing compiler we use under the hood. It's an incredible piece of technology. It's really, we're sort of feeding it these small little programs of one operation at a time, and it's doing, it's optimizing those, but it's really hungry, and it wants you to give it your entire neural network function, or maybe your entire optimizer step function. And because when it can see a bigger chunk of the program, it's going to be able to optimize the heck out of it and do more. So to give you some idea of JIT and how to use it, let's look at a sort of trivial function. This is just going to do some sort of element-wise operations. As I mentioned before, element-wise operations are the kinds of things we expect to be able to optimize. So we haven't used JIT yet. This is just to say we can write a function, we can apply it to inputs, we get device array outputs because we're doing sort of things operation by operation on the GPU. If we make the function g the JITted version of the function f, you can actually see that it'll have the same input-output behavior. If you want to like memorize, one of these numbers, we have the same input-output behavior from applying f to x as applying g to x. So in some ways, JIT doesn't change this input-output behavior. What does change is the timing, right? And so like here we see that we've gone from maybe 9 milliseconds to 350 microseconds. So pretty substantial speed up. And the reason for the speed up is, as I mentioned before, where instead of just doing things operation by operation, we're able to, XLA is able to fuse all these operations together into sort of a single kernel, which reduces the, I guess it reduces some, Python dispatch overhead, but more importantly, it actually reduces the amount of, memory transfers that we have to do. This is just a toy example. XLA is, as I mentioned, has a huge amount of technology behind it. And so, beyond toy examples, XLA is basically the fastest compiler for things like neural networks on GPUs and certainly on TPUs. So this is also, quite toy, but I just wanted to call out the point that JIT and grad are totally composable with one another. It's not shown here, but if you write functions, if you differentiate a function that lexically closes over some other values, and you're also, those values are participating in some outer differentiation or some outer JIT compilation, you should always expect Jax composition of transformations to work, including JIT with grad as many times as you like. And this is really important because it means that you can use JIT in your library code. It's not just sort of a top level operation. You should use JIT wherever you can. Usually at this point in the demo, I talk a little bit about the limitations of JIT. So JIT cannot compile all Python code. There are constraints in terms of what Jax can sort of like trace compile effectively from Python, and also what XLA can accelerate effectively. It's really a domain-specific compiler. I don't have time to go into those, but at the high level, I guess the idea is that you JIT the biggest pieces you can in your program, and it'll always be very loud about whether something's either completely compiled and staged out to XLA or it's not, and you'll get a loud error as soon as you try to JIT it. So skipping over the constraints of JIT, but just indicating that they're there, let's go on to another transformation. This one is called VMAP. It's a little hard to describe, but it rapidly becomes everyone's favorite once they play with it a little bit. So VMAP stands for vectorizing map. And to explain what it does, let's just look at another simple function. This function takes in a vector, and it gives us the sum of the squares of the elements of the vector. So we're familiar with this this kind of a function. I've written it so that it's not polymorphic in any way. It can only accept vectors. We know how to apply this thing, right? We can apply it to a range of integers, a vector of integers, and we know how to get the results. How would you apply this function to a sort of like stack of inputs? If you think of every vector as a single, maybe example, maybe we can create a stack of 10 such examples. How would you apply it to a set of examples? One way to do that is to write a loop, like a list comprehension, and then stack together the results. And this, of course, works and produces the right values, applying f to every row in this sort of matrix. But it's inefficient, right? This is sort of like saying the way I'm going to compute, the way I'm going to apply my neural network to a batch of examples is I'm just going to take out a single vector element of the batch at a time, run that through my neural network doing matrix vector products, then get the result, and then I'll proceed on to the next one and just have an outer loop. That would be nuts. Like no one would ever, run their neural networks that way. Instead, we want to, for efficiency, do matrix products, right? We want to sort of evaluate these operations on the entire batch at a time, and that way we'll, be doing much more efficient evaluation. VMAP basically adds batch dimensions for us. And so if you like, when I write vmap of f, then that gives me a new function that I can apply to a batch of inputs, in this case, to the whole batch at once. It's producing the same outputs, but it's doing it in a much more efficient way. It's doing it by plumbing the batch dimension through this function f, so that it can all be evaluated efficiently. To prove that to you, we can use this make Jaxper function, which is itself a very simple transformation, but it's a little pretty printer. And this one will just say like, hey, what does this function look like to Jax? And the high level point here is that instead of us having an outer loop passing one vector through at a time, what vmap has done is it's actually transformed that original simple function to say, let's push through an entire batch of examples. You can tell because we're saying now, instead of this reduced sum being on a vector, it's actually being applied to a matrix, like a whole collection of vectors, and that's why we're only applying the reduced sum along a single axis. So I mentioned that this becomes people's favorite. You might be wondering, like, well, I'm already used to like writing all my code with batch dimensions. I carry batch dimensions through all my libraries. I expect everything to have an explicit batch dimension. Maybe I don't need vmap. It's cool that it can add batch dimensions automatically. I would say vmap is especially interesting for adding batch dimensions to code that you didn't write. So actually, if you have someone else's library of Jax code and they didn't add a batch dimension in a way that you want, you can actually vmap their program and add a batch dimension. In fact, even better, there might be code that no human wrote that you want to add a batch dimension to, like if it's the result of autodiff. So I mentioned before, to get per example gradients, you can sort of just compose these two Jax transformations. You can vmap a gradient function. This is actually running on our previous example of our fully connected neural net. And this is going to be an efficient way to compute per example gradients. We don't have to step through this Jaxper, but this is sort of a fast way of doing that. Was there a question? I heard a thing on a microphone. Nope. Cool. I want to be mindful of time, so I'm going to but I want to be sure to cover PMAP because this is also very exciting. So I mentioned that we've been running these operations on a GPU, and that's true. But actually, the VM that we're running on has 8 GPUs attached to it, and so far we've actually only been programming one of them. How do we use multi-GPU setups efficiently in Jax? So to do that, we have this function called PMAP, which acts very similarly to vmap, except instead of sort of expressing a map and then plumbing the batch dimension, plumbing the sort of mapped dimension down through all the primitive operations in your code to vectorize things, PMAP keeps the parallelism, keeps that map at the top level, and will actually execute over multiple devices, so over multiple GPUs or multiple TPU cores. At a high level, it's very simple. It works just like essentially like a map or just like a vmap. We can say, take this function that element-wise squares things and then map it over this array of integers. This is actually running on all of the 8 GPUs. It's squaring one integer on each of the 8 GPUs and then collecting the result back together. So it's not a very, it's not utilizing these GPUs very much. But this is actually already programming multiple GPUs. These sort of values live in like distributed device memory. So they're sharded across the GPUs that computed the values. But you can treat these values just sort of like any old NumPy array. And Jax will behind the scenes be collecting results together onto one machine if you need them for something like plotting. Maybe a slightly more interesting example with a little bit of timing to prove to you that we are actually using these 8 GPUs. Here's a little snippet to generate 8 5,000 by 5,000 arrays on all of our 8 GPUs. So it's one 5,000 by 5,000 array per GPU. That's what this first line does. The second line is just going to say, hey, execute a multiplication on every one of these GPUs, each one acting on its own matrix. So if you pmap the np.dot, and then by pmapping np.mean, this is going to say, hey, compute the mean of the results, the element-wise mean of every matrix for every GPU, and show me the result. And just like that, this is computing the element-wise mean of these squared random matrices. This matrix that we've been operating on just looks like its logical shape is 8 by 5,000 by 5,000, even though it's distributed across all 8 GPUs along that leading axis. And we can time things, and this will you saw before that we were able to do matrix multiply of 5,000 by 5,000 matrices in about 19 milliseconds. This is just sort of a way of proving to you that we are actually using all 8 GPUs, because now we're doing 8 of those 5,000 by 5,000 multiplies, and we're taking about the same amount of time to do it. So PMAP is a way of, it's an easy way to express parallelism where you're just mapping a function across multiple different inputs. It can do a bit more, actually. You can write sort of SPMD programs, single program, multiple data kind of programs, like you might if you used MPI before. The idea is that you can do some kinds of communication, like through collective things. So for example, if you want to do an all reduced sum, for example, to normalize a vector, PMAP is the way to do that. I won't jump into the details here, other than just to say that like PMAP gives us a way to sort of express pretty sophisticated communication patterns in a really lightweight way. So for example, if you want to be able to do reductions along sort of mapped rows or mapped columns or both, PMAP is a way to do that, and it'll do it efficiently. So the last thing to mention is just that as I've been mentioning, you should expect to be able to compose up all these transformations together, and that's really where the power of Jax comes in. So in this case, here we've got a doubly nested PMAP, and you can see we have like a grad in the middle, sort of sandwiched between these two PMAPs. If you look closely, here's where we have some like lexical closure going on, this sort of thing. And this is sort of no problem for Jax. You can compose up differentiation, you can compose up PMAP. You can differentiate again from the outside. So this is like grad of PMAP of grad of PMAP. And everything sort of just works. In fact, if for sort of a less artificial example, here's a really fast way to compute Hessians that puts together all the transformations we've talked about so far. So it turns out the fastest way to compute a full Hessian matrix is to combine forward mode, that's a JVP transformation, and VMAP, together with reverse mode, that's this VJP transformation, with another VMAP, and that'll give us a fast way of evaluating Hessians, which, why not throw a JIT on the end to put it all together. So this is a way of, on this first line, we're just applying the Hessian to that neural network that we had before to get the input-output Hessian. In fact, we can then, why not throw another transformation on it? Why not PMAP it? So this is a way to get per example Hessians as efficiently as possible mapped over all 8 of our GPUs. These numbers, of course, are totally meaningless, but just to give you an idea of how these things can be quite practical. This is the fast way to compute per example Hessians in parallel. That's it for the demo. There are actually other transformations that are in the pipe. I will just very briefly mention them. There's one for sort of ragged batching of RNNs and sequence models, if you like. There's another one for exponentially faster, very high order autodiff. That's pretty cool. Anyway, so Jax, it's all about transformations. I think I'll probably call it there. I have some backup slides about how Jax works, but maybe I'll stop there and talk about if you guys have any questions, I'd be happy to answer them.
We were actually collecting some questions on the chat. So I'll actually read the question loud, so it'll stay in the registration, okay?
Yeah.
Okay, so by the way, can you stay a few minutes after 8? I don't remember if I asked you before. So if we don't have time to close all the questions now before the second talk, we can recover them afterwards.
Yeah, I'd be happy to.
Okay, so first question was, what kind of hardware or environment, clusters or multi-GPU machines does Jax target?
Yeah, great question. So I was showing you sort of multi-GPU setting. That was one node, if you like, one like CPU with 8 GPUs plugged into it. That's a common setting that's very easy to handle with Jax. Internally at Google, so also you can handle sort of one machine with multiple TPUs attached to it. Internally at Google, we do things at a lot more scale. In particular, we program TPU pods. And these look like multi-node setups in the sense that there's sort of multiple host CPU machines with TPUs attached to each one and some high bandwidth interconnect among them. Jax is really good at targeting those. It's actually like especially good internally, and it's not quite so good externally yet on cloud TPUs, just because there's other sort of TPU infrastructure that needs to be improved. But I guess the basic Jax system from our end scales out. So the sort of, I would say in the open source world, the sort of easy sweet spot is single machine, multiple accelerators, be they GPUs or TPUs. There is actually also sort of an experimental implementation of multi-node GPU support. So if you have a GPU cluster, so there's 8 GPUs on each machine for like 10 different machines or something, There's a way for Jax to target those, but it's not a very well-trodden path. I think there's probably some inefficiencies where the way Jax is using nickel for the all reduced collectives across machines. I remember there being some inefficiencies there about like communication not being optimally overlapped, that sort of thing. If you're interested in doing like large-scale multi-GPU programming with Jax, please reach out to us on our issue tracker or our discussions page on GitHub, because we sort of have this prototype and we're kind of waiting for someone who like really cares deeply about it to engage with it so that we can push it forward. So I guess the short answer is Jax goes to bigger scales, but it's kind of like mostly Google internal. You can use cloud TPUs for bigger scales. That's getting better all the time, and I expect it to get a lot better this year. And then the multi-GPU support across many machines is also sort of a work in progress. And please reach out to us if you're interested.
Okay, we have a second one from AGS test user. How do you compare with Torch that also makes gradient and operations on devices, and with Numba that also have GIT compiler?
Yeah, that's potentially there's a lot that can be said. I'll try not to be too long-winded. First, I'll mention Numba. Numba is quite interesting and actually in many ways complementary to Jax. So Numba was kind of like originally motivated, my understanding, by an escape hatch to NumPy, where you can write things in sort of the bulk array programming model of NumPy, but some programs maybe that you need to write as like scalar loops, the sort of thing, they don't really fit into the NumPy model very effectively. And so Numba and Cython and sort of thing grew as an escape hatch, where if you need to do things that really look like scalar loops, Numba was like your recourse to do that, and then you'd fold it into your overall NumPy program. In some ways, Jax is really about the bulk array programming model. Jax and XLA are about that thing. So it's like if you need to sort of like make a GPU or CPU kernel that does like scalar element-wise loops, you can't express it in terms of NumPy operations. That's what Numba is really good at, and Jax actually is not really good at that. Jax and XLA are not focused on that thing. So that's why I say they're sort of complementary. For the same reason you'd have an escape hatch in the NumPy programming model to say, well, I really need to get down into these scalar loop nests. There's a similar motivation for that kind of escape hatch in Jax. And so I think, I'm not sure if there's really any active work on it, but I think it's a really compelling thing to look at, because Numba can generate code for CPU and GPUs, I think, and because XLA can call into external code blobs, I think there's probably a way to hook these things up together kind of nicely. That said, Numba is only about code generation for programs that you write. It doesn't really admit transformations like autodiff. There's no Numba autodiff, and so it wouldn't be like perfectly harmonious in the Jax world for that reason. But I guess high level, you should think of these things as actually kind of different, like targeting different spaces. Jax is all about accelerating the bulk array programming model. Numba is about the sort of scalar loop model. About Torch, there's certainly much can be said. We collaborate with Torch folks and talk to them all the time. Yeah, I don't know. They're really quite different systems. For example, Jax is based on this theory that there are more transformations than just autodiff. I showed some like VMAP and PMAP, and mentioned some other ones and JIT. PyTorch is the design is sort of based on this idea of differentiation is sort of the only transformation, but let's implement that really nicely in like C++ and stuff. I think that we'll see how effective these other transformations are, but in some ways Jax is trying to be more general in that way. Also, our performance story is different, where PyTorch aimed at making dispatching kernels from Python, like dispatching a fixed set of kernels from Python as efficient as possible, because everything's like really well engineered C++. Jax has a different kind of performance model, which is use JIT to like, instead of just having a fixed set of kernels that ships with the library, be able to compose your own kernels, use the XLA optimized compiler to like build your own. And I think that that's like certainly an interesting, these are interesting points on the design space. A lot more can be said about like, PyTorch versus Jax. I think, some angles of comparison is like, see which one works for your work. I can certainly imagine work settings where one tool versus the other makes sense. I think, when libraries compete, it's a win for users, right? Like you should play us off each other and be like, well, I want to do this thing on your library, and then go to the other person and be like, well, this other library is better in this way. we are all trying to like, make things better, but for users, it's a very positive sum game where we're just like, providing better and better tools. Anyway, hopefully that was some kind of an answer.
Okay, we have, is it possible to use Jax with Pandas?
I think it would probably depend on the details about, what you mean by use it with. To the extent that pandas can speak NumPy arrays, then, these things can exchange NumPy arrays. Otherwise, there's probably a lot more detail. I guess, if you have something specific in mind, please open up an issue on our, or a discussion on our GitHub page.
Oh, I mean, you can also feel free to add something by voice now. It's gone. Okay, well. Next question was, is there any chance that Jax will support some sparse metrics in the future?
Yeah, I mean, that's certainly pretty interesting. All of our development is on the open on GitHub. And so like, you can see anything we're working on. We don't have any concrete plans about sparsity, but actually one of our newest team members is Jake Vanderplas, and he worked on SciPy sparse in past history. So certainly something that we'd love to support and work on. We don't have any concrete goals. I guess I would also say you can write a sparse library yourself, just like you can imagine writing a sparse library on top of NumPy, right? You can treat Jax like NumPy in that way and just say, I'm going to implement. It's not that Jax needs to learn about sparsity and these abstractions and these operations. I'm going to write a library on top of these things. And Jax is quite good at that because you can always use JIT to sort of like get rid of any sort of like zero cost abstractions, right? You can like JIT through all of your code that implements sparse matrices. So Jax doesn't need to know about sparsity if you're sort of implementing a CSR format yourself or something like this. So no concrete core support ideas there, but I think there's definitely cool libraries that could be written.
Okay, I'll actually read the last one so we can switch to the second speaker for 40 minutes. And then I see that there's another question. I also had a couple of questions, so we can move them after the second talk so we stay on time with everything. So the last question was, is Jax backed by NumPy in some way, or is it just an implementation of a NumPy interface?
It's the latter. It's implementation of the NumPy interface. Yeah, I hope I didn't go over time. But yeah, thanks for all the questions. I'm happy to answer more at the end.
Okay. Well, we move this one. Okay, so thanks for attending. I mean, it was a great talk, and I was really happy to have you here. And it's redundant now, but I am actually extremely happy also to have our second speaker, which is Michela Paganini from Facebook AI Research. Again, I'm very happy because Michela was also one of the first person to reach out for our association, and I mean, I love this kind of enthusiasm. So I'll leave everything to you.
Thank you. It's absolutely my pleasure to be here. Can you confirm that you see the slides okay?
Yes.
Okay, perfect. All right, well, thank you so much for having me again. My name is Michela. I'm a postdoc at Facebook AI Research here in Menlo Park, California. But I'm also an experimental physicist and an astrophysicist by training. So I was working at the Large Hadron Collider at CERN for about 5 years during my PhD on the ATLAS experiment. And so as you can imagine, I like working at this intersection of machine learning and science. I think both in one direction, especially as I did during my PhD, where I focused on using machine learning as a tool for discovery in the physical sciences. But then now also in the other direction, so using my physics priors and the tools from the sciences to work on what we call the science of deep learning. So to help us develop a more fundamental understanding of neural networks. So as I said, I started my career as a physicist, and I worked on many novel applications of deep learning to the Large Hadron Collider, and these included computer vision, mostly for particle identification type of stuff, generative adversarial networks for particle simulation, and so on. And I don't need to talk about any of this today, but if you're curious, you can always ask me about it in the future. But what I really want to talk about today is neural network compression, and I'm glad that it sort of came up in the questions already, but I mostly want to talk about how it can be seen not only as a very convenient way to deploy smaller sparse models, but also as a way to better understand the inner workings of our neural networks. You're probably all aware of this. Neural networks have been massively growing in size over the past decade, and some of the newest state-of-the-art models are getting into the 500 billion parameters or even more. And in a way, thankfully, we've gotten past the usual folklore that when a network is too big, it will certainly overfit. That's a very simplistic view of things, and the full picture now we know is much more beautiful and much more complex. So there is a lot of interesting stuff happening in this over-parameterized regime. So if that's the case, if there are all these benefits, then why has so much work focused simultaneously on reducing the size of the networks and creating more and more efficient ones as opposed to just bigger and bigger ones? And so, of course, there are many advantages and disadvantages from the practical standpoint to having small neural networks that perhaps have a clever sparse architecture could be. So simply put, first of all, from the point of view of storage, there could be app store limitations, for example, like there could be size requirements on the apps that you ship, download size, time requirements, so on. And training can also be sped up, of course, depending on the compression method that you use and the type of hardware that you use, and that could allow for much more frequent retrainings, especially to capture maybe some of the latest interests and trends in your data. Inference on top of training can also be sped up, once again, with the caveat of, it depends on the type of compression and the type of hardware that you're using, but this could be useful to reduce latency for real-time applications. And then compressed models can run on the edge, so on mobile phones or VR goggles like Oculus or IoT devices, and this could help address some of the privacy concerns around deployed models. There are power and energy saving arguments to be made. We can reduce the energy consumption and increase the battery life. We can enable computation on low power devices and also reduce the heat dissipation if we're talking again about wearables for users' comfort. And of course, there's a monetary cost associated with training and using these huge neural networks, and it has really concentrated the power in the hands of, unfortunately, a few users who've had the privilege to be able to afford this. But then most interesting to me, finally we get to this, compressing models, I think, can give us a better understanding of what parts of the networks are responsible for what parts of the learning process, and really challenge our notions about trainability and dynamics from a science of deep learning standpoint. And these are just some of the advantages. Of course, there could be more, but there are also disadvantages as well. For example, the absence of mostly pre-trained compressed models, which therefore causes us to have to retrain these models from scratch, which ultimately might be even more time-consuming and energy-consuming than just fine-tuning a pre-trained model that you might find in the uncompressed world. And then there are concerns that I feel very strongly about the fact that performance loss in compressed models is oftentimes just quantified in terms of an overall accuracy drop without really paying attention to all of the adverse consequences and the impact that this could have on underrepresented classes and outliers or forgettable examples. And then, of course, modern hardware, as we know, like the access patterns and the accelerators themselves have been optimized with this dense computation in mind, so without the compression part of it really in mind. So again, we would need new sparse kernels and custom hardware perhaps, or just different linear algebra libraries to power the compression and take full advantage of a prune model. So I think it's good to keep in mind both advantages and disadvantages to make sure that we don't fall for those like X is all you need type of solutions to what is instead a much more complex multi-objective problem. So now you have a better sense of the why we would care about compressed models. Let's now focus a little bit more on the how. So I like to say that there are constructive and destructive approaches to efficient model design. So on the constructive side, you build a model from the ground up by carefully adding and positioning parameters and operations in very clever ways, either through your inductive bias, so human ingenuity, or potentially automatically in a neural architecture search or AutoML type of way. And you can put all sorts of things into this bucket from using convolutional layers as opposed to the less efficient fully connected layers when the problem calls for it, all the way to the design of ResNet and ResNext and DenseNets, and even randomly wired neural networks and so on. And then there are destructive approaches, which is what I've been focusing most on personally. And these can include knowledge distillation from a teacher model to a student model, quantization or binarization of the weights in your model, and then finally model pruning, which is something that I'll talk about in more detail. So what is pruning? So simply put, pruning is just a way of removing unnecessary stuff in a network to try to reduce it in size. Of course, that's a very vague definition. What type of stuff and structure are we talking about? Are we removing entire neurons or only some of the connections among these neurons? And how do you define unnecessary? How do you know what's needed and what's not needed when we don't have a solid theory of how things really work inside of neural networks? And a nice connection that I like to make at this point is, if you think back at connectionism, which is where modern deep learning really came from, it was all about understanding how the structure of the connectivity pattern plays a role in the emergence of intelligence. So this is something that I find to be really fascinating. And pruning has been a very common model compression technique used in machine learning for multiple decades now, starting from the literature, as you can see on decision trees, pruning, all the way to the earlier work on neural network pruning from Young LeCun and others. You know, you can think of the optimal brain damage paper, the optimal brain surgeon, and these often come in the context of generalization, interpretability, and a lot more. And then over the years, of course, researchers have come up with many different ways of identifying superfluous information, or superfluous portions of the model, which have resulted in just as many different pruning techniques now out there. And I like to classify these in a taxonomy of pruning techniques that can vary along a variety of different axes. And these axes can include the nature of the entities to prune. So are we pruning connections, nodes, layers, channels, the choice of proxy for importance of these entities. So are we talking about their weights, the activations, the gradients associated with them, how to pull together these entities for comparison. So are we comparing all the units across the same layer, or all of the units across the whole network, or other options perhaps, when to prune, so during, before, after the training, whether the prune entities are pruned forever or whether they can be reinstated at a certain point during the process, whether we're applying hard pruning, so with like binary masks, or soft pruning, iterative or one-shot pruning, and even what to do with the network once it's been pruned. Are we fine-tuning it, reinitializing it, rewinding it, etc. So let me just visualize at least one of these dimensions of the decision space, which has to do more with the order of the operations. So normally, when we are in the business of building a new neural network and training it from scratch, we just initialize it, and then we train it according to some training procedure, and that's pretty much it. Then when we look to adding pruning to the process, most of the pruning techniques historically have acted on some pre-trained network, so after the training phase. Now, after pruning, usually you don't leave the network as is. You tend to want to fine-tune it or partially train it again. And this can generate even a loop of training, pruning for a certain number of iterations. And this iterative pruning and fine-tuning technique has really been the leading procedure up until very, very recently. Another thing that you can do is to extend the reach of this loop. And so instead of simply continuing to train the net after pruning, as we did in the fine-tuning example in the previous slide, what you can do instead is to decide to rewind the weights of the prune model all the way to their initial values and retrain from there. Retrain and then prune again, perhaps in an iterative fashion, or one shot if you prefer. And this is exactly what the lottery ticket hypothesis, at least in its original formulation, advocated doing. And then just as an aside for completeness here, I'm not going to talk about it enough, unfortunately, in this talk, but I want to mention that there is also another way of including pruning in the loop, and that is when pruning happens at initialization. So prior to any of the training, and this again can be one shot or iterative pruning, so that the network that you end up training is already compressed. And of course, there are also methods that simultaneously include the training and the pruning, perhaps imposing some sparsity, inducing regularization, or something like that. Okay, so now that we've introduced pruning at a very high level, we can go into part 2, which is more of a research review involving some of the pruning techniques. And what I'm really interested in is really, again, pruning as a scientific tools to better characterize the deep networks and different regimes. And my starting point was what's been known as the lottery ticket hypothesis, which is just one of the many papers, but probably the first one in this direction to identify some perhaps counterintuitive phenomena in proof networks that I thought were worth investigating. So let's first talk about what the lottery ticket hypothesis is and what it says and why it's important. So this work is famous because it provides the first empirical evidence that demonstrated that certain small sparse networks can be trained from scratch to very, very competitive accuracy or performance in general, despite having a very low number of parameters. And this sort of goes against our usual notion that networks with fewer parameters aren't as powerful, or at least shouldn't be able to reach the same levels of accuracy as networks with, say, like 10 or 100 times the number of parameters. But this work also provided an algorithm to find these lucky subnetworks, and this involved iteratively pruning and rewinding the network, starting from an over-parameterized network, like one of the usual networks that we tend to use. And also, just as an aside, why is this called the lottery ticket hypothesis? So it's an analogy that they make in the paper. So they say if each random small network is a ticket in a lottery, the probability of sampling a winning one that in this case trains to good performance is very low, like winning the real lottery when you only buy one ticket to it. And the authors explain the importance of over-parameterization in terms of buying so many tickets to the lottery, which is effectively what you're doing when you over-parameterize, that your probability of now winning the lottery is really high. So that's very interesting because I think that this conjecture says that over-parameterization is not needed to simply just get the behaviors that we've come to want and expect out of our networks, because there exists some small special networks that can give us those benefits as well. So we might not need over-parameterization after all. But the problems are that A, we don't fully understand why that's the case, that these small networks work, and B, the iterative pruning technique that is suggested is quite expensive from the computational standpoint, because it requires restarting and retraining to convergence every single time. So research over the past year or so, including research that I've personally been involved in, has focused on ameliorating these two shortcomings. And as you can see, really stress testing this hypothesis and improving this iterative algorithm has been at the center of a lot of exciting research at FAIR. So our group has put out many papers trying to tackle some of these open questions around lottery tickets. And today I want to discuss just a few of them, but there would be dozens from all sorts of other groups as well, and this slide is a little bit out of date already, so there's even more just coming out of our lab. So let me talk about a few recent key findings, which, if anything, I think they will show you just how slow progress tends to be in research when your goal is really like to get a fundamental understanding of something as opposed to just beating, some benchmark or state of the art on a task. So first of all, one of the two contributions in the original lottery ticket paper. So we had the observations and the algorithms. Of those two, the one that we started picking apart was the algorithm. So we started asking whether there is something special about that algorithm that they proposed, or whether any other pruning technique other than this magnitude-based iterative pruning that they used was able to identify winning tickets. And the answer turned out to be yes. So here on the left, you see the test accuracy achieved by prune models as a function of the sparsity, or the fraction of prune weights for a series of different pruning techniques. And what you can see is that many of them are capable of finding competitive subnets that train to very high accuracy, even at very high sparsity levels. And so as a consequence of that, we asked, okay, so do all pruning techniques effectively find the same lottery ticket, or are there many different lottery tickets that can be found within the same architecture? And the answer turned out to be that each pruning technique actually ends up finding quite different lottery tickets. So there is more than one. And therefore, we should be extremely careful before we dive into overanalyzing the properties of just one of them without understanding the broader picture of how it fits into that. And on the right, in fact, here you see how quickly the distance between these subnetworks grows as the sparsity increases. And this is just for like one of the layers of the Linnet model for one of the tasks that we were doing, but you kind of get the point. And by the way, not only are the architectures different, but also the functions that they learn to represent turn out to be different, and we have some results on that. So there is a possibility of perhaps ensembling different lottery tickets found within the same network for some performance gains. Okay, so there exists multiple winning tickets per task, depending on the pruning technique that you use. But what about lottery tickets on different tasks? How similar are they? Are they similar at all? Can I successfully train a lottery ticket on a task that it was not sourced from? And the answer here, once again, is yes. So lottery tickets seem to be relatively transferable in the sense that they can be retrained from scratch on a completely different task that is still within the same domain. So here we're mostly talking about academic computer vision type of data sets from the natural image domain. But yeah, the answer would be yes. So you don't have to source a new one on every single data set that you want to apply this to. And also tickets that were sourced on harder tasks such as ImageNet tended to transfer better to easier tasks than vice versa. So once again, we asked, is this thing that we observed because the lottery tickets that were found, again, by the same pruning technique this time, but on different data sets, are they essentially identical? So do they just trivially transfer? And the answer here is no. The masks that define this sparse connectivity of the subnetworks that are found on different tasks are actually quite different. As we've seen before, for example, when we were holding the data set fixed and then we were varying the pruning technique. So here too, the distance between these masks tends to grow as the sparsity increases. But do they become completely different? Do they completely diverge? And I think we can zoom in for a second. So if these are very high sparsity networks, so iteration 19 of pruning corresponds to about like 99% of the weights being gone, being pruned. And so the number of remaining weights is very low, maybe around like 700 or so in the network that we were using. And these masks, as you can see, are not completely non-overlapping. So even at such a high sparsity, there is still some overlap among these masks that sort of, we thought, identified a core shared part of the network that always goes unpruned, like always. And so we were like, okay, wow, this might be interesting. Let's start looking a little bit more into it. And so we find that this core part of the network, this intersection of some masks that are sourced over different tasks, is itself a sparse subnetwork that trains to very high levels of accuracy. So by definition, it's itself a lottery ticket. And one practical advantage of finding lottery tickets in this way is that we can use this as a shortcut to finding high sparsity lottery tickets. So if you think back at the original iterative pruning algorithm, that was very sequential in nature. So instead, here, instead of finding a single lottery ticket after, say, 20 iterations of pruning, you can find some low sparsity networks over multiple tasks, and low sparsity could be like just 2 pruning iterations, and do that in parallel, and then just take the intersection of these masks to find a high sparsity ticket that has very similar properties. So as we said, this intersection ticket is capable of achieving similar performance to some equal sparsity traditional lottery tickets. But it also does appear to have some potentially advantageous properties that we want to dig deeper into in the future. So from the trainability standpoint, for example, the remaining weights at initialization are not as far away from 0 as they tend to be for lottery tickets that are found through this magnitude-based pruning that was initially proposed. And so this might be promising, we'll see. So at this point, you might be asking, okay, so what's the significance of this core part? Like, why is it important? What's it doing? Unfortunately, the answer is we don't know for sure yet. There's still a lot of research that is going on. So hopefully, in a few months, I might come back and give you a talk and let you know how that's going and what we've learned. So it's a very slow research process. So I just flashed a few high-level research results that were enabled by pruning. But to go back to maybe to tie a little bit more with the first talk that we had today, of course, none of this would have been possible without robust software tools that were powering our research. And one of these tools was the pruning module in PyTorch. So we contributed this to the core library as a result of this very fast-growing interest in pruning research. And I think hopefully this might be more interesting to you perhaps than a bunch of open question and half-answered questions on the research front. So let me tell you a little bit more about how PyTorch pruning really works and how it can be used perhaps if you want to explore pruning in your applications. So the first thing that you'll find in PyTorch pruning is a base pruning method, which is an abstract class that provides a skeleton for all of the pruning techniques, and it implements a variety of shared functionalities across all of them. And then all of the pruning methods that are currently available in torch.nn.utils.prune are listed here on the right. And these are all derived class that inherit from the base pruning method. And these include a pruning container that we can discuss later on, but it basically just handles the successive iterative pruning part, so combining multiple pruning calls together. And then we have a variety of random and magnitude-based pruning techniques, either structured or unstructured. So this means either channel-based or connection-based, more or less. And then we have a custom pruning class that basically enables you to apply any user-provided mask that you might have found through some neuron importance technique that you design, maybe. So we want to look at how it really works down, in the back. So we can start from the core functionality, and that's the mask computation. So, and by the way, I talk about masks because the way pruning is implemented right now in PyTorch pruning is by applying a mask onto the tensor that we want to prune. So in other words, we don't physically remove or drop connections or neurons. We simply generate and store a binary mask that identifies which connections are present and which ones have been pruned. And so the way that this mask is computed is, of course, unique to each pruning technique. So the base class just defers to the subclasses for this implementation. And then to compose multiple pruning calls, we make use of a set of this pruning container, and that stores the history of all of these calls to be able to combine them and apply them correctly while keeping track of all of the masks that have been generated before. So once the mask is computed, the design decision was how to store this mask and how to correctly apply it to the forward and the backward propagation. And so the choice that we made in PyTorch was essentially a reparameterization in terms of the binary mask. So the binary mask was stored as a buffer, and then there was the original weight parameter, and then a multiplication of the two gives you the prune weight to use in the forward. And what ensures that this reparameterization is correctly applied before each forward call is the forward prehook in Python and PyTorch jargon, and that basically just multiplies the two together before they can be used to process the data. So this module, so torch.nn.utils.prune is designed to act on a torch.nn.module so that it can attach these buffers and prehooks and whatnot and modify the parameters as we just talked about. But if that's not good enough for you, we also have a lightweight interface that allows you to prune independent tensors that are outside of the construct of a network or a module in PyTorch. And if you want to instead prune the whole network, that's just as easy with a few lines of code. So we have an example, for example, at the bottom of the slides here, which show how to prune multiple layers simultaneously, perhaps all of them in a network, by specifying which parameters we want to compare for pruning, and then calling this global unstructured pruning technique that is provided in torch.nn.utils.prune. So this just wanted to be a super quick primer, but if you are interested in PyTorch pruning, absolutely feel free to ask any question later, or I would recommend that you check out the tutorial that we contributed. So now that we have all these tools at our disposal, I think we ought to use them carefully and responsibly. So most papers that you'll read in the pruning literature will tell you something like, oh, this technique that we come up with, like prune 99.9% of the model, only losing 4% accuracy, say. And the issue that I have with these statements is that they rarely investigate what this like 4 or whatever percent accuracy drop really means when it comes to the classes and the individuals that might be affected, especially if we're talking about models that are deployed in production. So 4% might sound like reasonable as a compromise if I can get my model size down that much. But what if that severely affects the fairness of the model? So in this pruning responsibly paper, we investigate in some canonical image classification scenarios how pruning actually reduces the per class accuracy, among other things, as opposed to the total accuracy. And we notice, of course, that different classes are affected differently by pruning, as one could have assumed. And in particular, unfortunately, underrepresented and more complex classes experience larger relative drops in accuracy. So we looked at this not only at a class level, but also at an individual level. So if you look, for example, in the third plot from the left, there is a little dot in the bottom right. I don't see if you see my cursor, and I definitely don't see it. But if you look at that little red dot in the bottom, that is one person, one individual that contributed some data to this task. And prior to pruning, the model had perfect accuracy on this data point, on all the data produced by this user. After pruning, instead, awful accuracy. So it's really important to see that the way you intervene on your models, every single engineering decision that you make, for as benign as it might seem, for example, in the case of pruning, it seems pretty uncontroversial. Why should we not do it? It might actually really affect your end users. So please do so carefully and responsibly. And so just to have a few closing remarks, if we think at, back in the 80s, people had already realized that it takes more computational units to learn a solution than it does to try to implement it directly, meaning that over-parameterization is something that is beneficial and it's needed to simplify the learning or the optimization problem, but it's not necessary from a solution representation standpoint oftentimes. Today, I think we are already moving beyond that understanding and pushing it forward. So we understand that the learning itself perhaps doesn't quite meet that level of over-parameterization that we are used to using either. So it's not the representation, maybe it's not the learning either. And that's because perhaps there exists some smaller and sparse networks that are efficient and that are capable of not only representing, but also learning such solutions from scratch. And of course, as you've seen, we have a long, long way to go before theory and experiment can really give us a better understanding of how to enable efficient pruning, efficient training, and also inference, really. But we're learning something every day, and this is a very exciting field of research, and hopefully it will translate into benefits on the production side as well. If you're interested in pruning research or product application, feel free to get in touch at any point. Thank you so much for your attention. And if you have any questions, I'm absolutely ready to take them now.
We have actually a couple on the chat, so maybe I'll read them just like I did with Matthew, so they'll stay in the recording.
Mm-hmm.
So the first one was, as we witness natural language networks becoming more and more massive, pruning appears to be needed also in NLP. So most applications come from the CV realm. Are there significant results in NLP already? And in case there aren't, why?
Yes, absolutely. So I don't particularly focus on that. And so that's why my presentation has focused so much on computer vision. But there is, for example, a paper out of our group that applies lottery tickets specifically to RL, reinforcement learning, and NLP in relatively simple tasks at that point, but also it was kind of like groundbreaking at the time. I know of a lot of pruning and lottery tickets work happening in transformers, BERT-like models. It is definitely happening. Unfortunately, I'm not the best person to talk about them, but it's out there. I also assume that there are some complications on that front, though, because I think it's well understood that in computer vision, the type of models that we are using are so vastly over-parameterized with respect to the tasks that we're trying to solve, which, objectively, if it's image classification, it's relatively easy. If you start going into, segmentations and stuff, maybe it becomes a little bit harder. But in NLP, we're talking about extremely complicated tasks, and we don't have a sense as to how over-parameterized, if at all, our models really are with respect to the difficulty of those tasks. So there might be differences actually between the domains.
Okay, the second one is it possible that the occurrence of dominant subnetworks is related to the minimization method at training time?
Is it possible that...
You can read it in the chat.
Is it possible that the occurrence of dominant subnets is related to the minimization method at training? Oh, yeah, so yes. So another thing that will affect, of course, like the type of subnetwork that you find is, of course, the optimization strategy that you use. So we, in the first paper that we had about lottery ticket transferability, we investigated, unfortunately, only like SGD and Atom, and we noticed that tickets do transfer. However, once again, same thing as in for the tasks, they end up looking quite different. So of course, yes, that's yet another dimension of this entire, very entangled problem of initialization, optimization, task, and so on, that gives rise to slightly different masks and slightly different structures.
Okay, wait, I'm getting lost. Okay, is the pruning strategy a well-posed problem?
I'm not entirely sure what that means. Which pruning strategy to use? Is that maybe if the person's still here, they can
yes.
specify exactly what that means. Well posed with respect to what?
To the input data.
So which pruning technique to use if you have a specific type of data?
No, I mean, if you change a little bit your input data, is it the dominant subnet the same, or how is it influenced by the data, the input data? Can you ensure that there is a continuous dependence between the data and the subnet the dominant subnet that you get?
Yeah, so we didn't try to interpolate between them. So we completely switched. We took like a very discretized approach. So we just changed data set completely, went from MNIST to Safar to whatever. If you just slightly modify your network, I don't exactly know. Sorry, not your network, your data. So if you slightly perturb it, how does that affect? So that's a good question. I don't know the answer to that necessarily.
We have another question in the chat. So what about nodes neurons pruning instead of just weight pruning?
Yeah, so that is what I usually refer to as structure pruning. So that's when you prune entire neurons or channels, as opposed to unstructured pruning, which is where you just prune individual connections. Both of these are extremely common. Of course, structure pruning might have some technical, practical advantages in terms of then re-implementing the network in a more efficient way, without necessarily having a fully sparse, Gruyere-like type of network. So so both of them are valid. There are advantages and disadvantages. Unstructured pruning seems to have higher performance in the end. So for a given level of sparsity, the network might be more robust to unstructured pruning, so removal of connections. But again, it depends on why are you even pruning to begin with. If you're pruning to remove entire channels and neurons, then you would want to do structure pruning. You'd have to be a little bit more careful, but it does work and it is used.
Okay, I'm not sure how you are with time, so it's 7 to 8. Are there other questions? Also, feel free to speak up at this point.
There's another one that just came in. If we apply online pruning, like pruning while training, will the final network work well for transfer learning cases as the network with no pruning? I am not entirely an expert in online pruning necessarily. I don't know how that would affect the type of network that you end up with, as opposed to pruning entirely post-training. So basically this would mean, I'm assuming it would mean pruning after maybe a batch or one epoch, and doing so without getting to convergence every single time, but perhaps without the rewinding. I honestly don't know. There's so many moving parts in this. I think the right answer, to be honest, is also, it depends on the application. It's very application specific. So I would refrain from giving you a particular recipe on how you should prune. So take that maybe with a grain of salt.
There are actually another question and a remark on this one. So the first one is, I work with tensor factorization methods to compress neural networks during my master thesis. I guess pruning got more popular and successful now. Do you see this area of research to be saturated soon, or do you see a lot of room for improvement in the future? So which is actually, do you see yourself out of a job soon, or?
Gosh, hopefully not. I mean, it's hard to say. I think one advantage, I think, in fact, maybe like tensor factorization as well, could be used not just for application purposes, but again, if there is a scientific question backing the progress, then I don't think we'll ever be done asking scientific questions. So from that standpoint, there is always work to be done. I'm not an expert in tensor factorization, unfortunately, so maybe I can't comment on that necessarily. Are we pushing the limits of the applicability of pruning? That's perhaps a good observation, but I think like understanding maybe also the interaction of quantization with pruning, and so all of these different pruning techniques and how they work together, maybe we can push the performance even further.
There was a remark on the previous question. Can pruning introduce a dataset bias?
Pruning certainly is data set specific, as we've seen. So if you run the lottery ticket finding algorithm on a specific data set as opposed to another one, you'll find different subnetworks. These transfer relatively well, but we haven't done a full investigation in terms of bias and fairness and how things are actually effective. So we say like, oh yeah, you get roughly the same accuracy, but to be honest, that's not a good enough answer. Beyond that, I mean, in this pruning responsibly paper, we did certainly find that, at least in the cases that we did study, pruning does act on the data set, on the individual data points in the data set, or in subclasses or subgroups in the data set in very different ways and in very non-trivially different ways. So there is certainly some bias that is being applied by the pruning that we don't necessarily fully understand.
Okay. Do we have time for a question myself? So I know you didn't talk about pruning at initialization, but do you think do you think there will always be a gap between, let's say, pruning before training and pruning during training, or is it actually possible to move everything during initialization? I mean, this has always been my one of the things I've thought about most.
I mean, I kind of hope so. That's something that I'm trying to explore right now. I mean, there are already great papers out there to do so in a principal way. So they use, so for example, there is very recently one called Force, there's SNP, there's GRASP. There are various different acronyms, of course, for these methods, and they use principal approaches to deciding which things should be pruned before you even do any of the trainings. And they seem to work really well already, so like, we already have a pretty good, solid basis. Is that competitive with post-training pruning? Probably not yet, but I honestly haven't personally done the comparison. There is certainly room to improve even there, because these are just very principled approaches, but you know, perhaps we can try to learn what to pick out. And I think there is room for that, because one way of thinking of overparameterization is that it models the loss landscapes in such a way that you will sort of always find a very competitive point to converge to that is close enough to the initialization. And so if you're able to then remove all of the dimensions that aren't needed to go from the initialization point and traverse that loss landscape down to that really good minimum, then you should be able to navigate to there anyway. So I think it's a really, really exciting and promising field. I don't know if we'll ever fully close the gap, because it will always have less information, of course, but it's just how much less information.
Okay, I think it is the first time we stay in perfect absolute time ever. So it's an accomplishment for everyone. So thanks again for the great talk. And I don't know if there were some, if there are, do you still have time, or do you have to?
I have to run, unfortunately.
Okay. Then
maybe I'll let you and Matt chat and everybody else.
Are there still questions for Matthew, or?
Everyone.
Bye. Matthew, are you there?
Yeah, I'm here.
There was actually one last question for Michaela, but she lost it. I actually missed the question before, but I have to find it again. So how does Jax integrate with other languages, more specifically with Julia?
Yeah, there's no, I don't think there's any one, concise answer. There are, I mean, like on the social dimension, there are definitely folks on the Jax team who have used, Julia for a long time and have Julia stickers on our laptops. I actually went to Jeff Bezanson's thesis defense on Julia. He was like, one of the Julia creators. And I was there in person. So yeah, we've been fans of Julia for a long time. As far as specific interop, it's just sort of, general ecosystem stuff where like, Julia has ways to call Python and NumPy code, and Jax will work that way. So there's definitely ways to, actually a collaborative mind on a preprint we just put on archive used called into Jax to do this like very high order autodiff stuff that I alluded to. But then was calling into it from Julia because he had all this plotting code in Julia. He's a big Julia fan. And so that was like Julia calling Python. And that, worked fine. It just depends on what you want to do, like how you want to rig up these systems. For other things like, interaction with PyTorch, for example, both libraries implement the DL-pack standard for like 0 copy handoff of arrays on GPUs. And so in principle, this means that, you can do 0 copy interop and have some, call some functions in Jax and call some functions in PyTorch and have them be efficient. I think there's still some things to improve there to do with like device synchronization. Actually, there's a discussion thread on our GitHub page right now about that. But yeah, anyway, I guess, our philosophy in Jax has always been to, try to, don't try to be a monolith. Don't try to like solve everyone's problems and say you have to use our thing. We are very keen to interoperate with other systems, be them Julia or PyTorch or whatever, and just make those, make those paths efficient for our users. So anyway, yeah, if you have a particular kind of interop, you'll probably, have to pave some paths yourself, but come to our issue tracker and ask us about it, and we'll be happy to help with it.
Okay. Are there other questions? Yeah, I think there's not a lot of people now, so you can speak up. In the meantime, I do have one question. So I see that there were now a lot of high-level framework on top of Jax, IQ. I mean, there were quite a lot of them. But it seems that a lot of them just try to replicate higher level interfaces of other libraries. Like, let's try to make a Keras on top of Jax. But they're different philosophy. I mean, one is functional, one is more object-oriented. Do you think it makes sense to have this sort of high-level interface on top of that, or no?
Yeah, right. I think, there's a few angles on that question. One is like, hey, when there's 1,000 flowers blooming, then it's like a paradox of choice for a user who just wants to like, get their work done. How do they know, which library to use first? I think everyone has like, JavaScript libraries. There's like this huge proliferation and they're different every year. And, it's hard to choose among them. I think, yeah, there's a siren outside, by the way, it might be loud. So, I think in general, our stance on the sort of like Jax core team is we're trying to build, a focused library that's just working on the sort of like numerical basics and transformations. And part of that is making it be a great platform for other libraries to build on top of. And so we don't want to solve the sort of neural network higher level API problem ourselves, but we want to be a great platform for people to write their own. I think that there are some really great ones. I think the situation is fluid. The situation is evolving where there might be some amount of things might coalesce. I don't think it's actually a solved problem. I mean, I think you kind of alluded to is this just replicating existing stuff? And I think not. Actually, I would push back on that and say that I think Jax does some things quite differently. For example, with VMAP, you actually don't have to write your libraries with batch dimensions. And actually some of the libraries like out of DeepMind have no batch dimensions anywhere because they know that a user or a library calling it can always VMAP things and get the efficiency. I think some things like VMAP, like other sort of Jax transformations, even just the angle of using functional programming are actually new ingredients that like might change how we write neural net libraries. I think people are still figuring things out. The existing Jax higher level libraries like Flax, Haiku, and Trax, and there's some other ones out there as well. They are actually exploring slightly different points in the design space. I don't think we know yet whether there is like one true optimal point in the design space, or whether that things will converge to, or whether there will be different tools for different jobs. We're kind of just like aiming to support these things being written. I guess I would also add one. Jax is really focused on researcher use, and I think researchers are often building new things, and oftentimes sort of existing fixed libraries might not be sufficient for their purposes. And that's why we think sort of having many libraries, while it might be frustrating, especially to sort of a practitioner doing applied machine learning in an industrial setting or something, might be annoying to say like, well, there's all these libraries, I don't know how to choose among them. Actually, I think that for research users, having several different tools, they might grumble about not just having one that solves everything, but oftentimes like different researchers will choose different tools for different tasks. I personally always wrote my own libraries from scratch for the problem that I was working on. And that was actually part of the fun and part of the like learning process to understand a problem. So anyway, there are a lot of higher level libraries to do with neural nets. I guess one last thing to say on that is there are higher level libraries that don't have anything to do with neural nets, actually. There are higher level libraries around robotics or molecular dynamic simulations and these sorts of things. And we're trying to take a broad view. We're not building a system just for neural networks. We think it's really great for that, but we also want to enable these scientific applications, or probably things in convex optimization or something. So in some ways it would be almost like a type error to say like, why not build the neural net higher level libraries? We're trying to do more things than just neural nets. We're not trying to just specialize on neural nets. So I think those will always be sort of like outside the Jax core mission. But I think they're turning out pretty great, and you should give them a try.
Okay, thanks. Very detailed answer. So if there are no other questions, I think I can thank you again. You had a lot of thanks, both the speakers in the chats. I think they were both very, very interesting talks. So thanks again. And this was also our last meetup before the holidays. So good holidays, everyone. And we'll start again with our meetup in September. And in the meantime, you can follow us on the social media or everywhere. And of course, we'll send the material to everyone. So if you can share the slides or anything, and we'll upload the video, and you can, we'll send them to everyone. So thanks again to everyone. Bye.